So turn it off. The manipulated variable is what turns this to an on-off control. Notice it says on-off control, not on-off measure. It could be on-off measured, and that's your upper and lower levels, your watermarks. But the manipulated variable will always be on-off if it's an on-off control. If it's proportional, it will be a proportional control. And that's just simply is a description of the same thing. And so most of what you're going to see in 7, when it comes to on-off, is a description of this. Now, talk about deadband here. What sets the watermark is our tolerance for deadbanding. As we're empty, we turn on some sort of a fill mechanism or turn off a drain. We fill up, we get to the top here, we turn off that fill, or we turn on a drain, go back down. We have an on, off, on, off, on, off. When we have that sort of control, we look like this. If we want the effect of a 50% fill, then it's half the time on, half the time off. If you want a 25% fill, a quarter of the time it's on, 3/4 of the time it's off. So we can set our percentage by what percentage on it is. We see things like this. You have a stereo system, like for cars, big loud system. Surprising enough, the way the sound is done is exactly this. It's not linear, it's on-off. Why on-off? Electronics, when it's fully saturated or fully off, uses almost no power internally. So all the power goes for output usage. Transistors in linear mode only output about 25% efficiency. Burns up a lot of excess power. So if you have 100 watts going into your stereo, and it was what we call Class A stereo, which is the old time 1970s, 60s, 50s type amplifiers, if you got 25 watts, it was amazing. Usually they're more like 10 watts or so. They're pretty high in efficiency, a lot of heat coming off the bot. Now you use what's called Class D amplifiers, which is what's switched on and off in stereos, and if you have 100 watts going in, you should get about 97 or 98 watts out. The amplifier runs much cooler, less power wasted, which means less dissipated as heat, and you get a whole lot more louder sound. That's why people carry boom boxes now. When I was a kid, their stereo systems were massive, expensive, it cost a year's salary to get a good system. And they were big boxes and lots of heat off of them. They're good room heaters. Effectively. Nowadays, and you had to have big stereo, the sound just wasn't good. Nowadays, boom boxes do a fine job there, or even your telephone does a fine job of music. Because the Class D, it doesn't need to be that big anymore because we're not dissipating, wasting heat. We're just switching. This is an efficient way to go because we don't have an in-between. It's kind of like power, voltage times current. It's when you're in the middle is when you use the most power. Because if it's all voltage, no current, there's no power. Volts times 0 amps is 0. If it's all current, no voltage, there's no power. Amps times 0 volts is no power. It's when it's in the middle between the two, that's when you get your maximum power. This is the extremes. It's the least amount of power wastage, least amount of control wastage. It does work that way. The difficulty is you get this large, what we call deadband. In other words, the level in the system we have won't necessarily sit at 3 inches. It'll go back and forth between, say, a low of 2, a high of 4, and you'll see the level change like that. Now, if you can tolerate that, not a problem. If you can't, what's the solution? Narrow it down. Now, it's easy to see in the tanks we have here, to reduce the deadband, you literally take those 2 switches out there and make them at a slightly same level, closer together, and that would narrow this. If you can tolerate a wide swing, leave them apart. Now, what's the problem about too narrow a deadband for level fill? Not necessarily this way with the drain, but particularly when we have a pump involved, what would be the difficulty? Stressful in the pump. You start a motor up, that's a lot of power. So the more often you turn on a motor and turn off a motor, it really stresses the motor. At startup, that chews up motor. That burns up the motor. So the less you start it up, the more efficient it's going to run. Now in the case of heat elements, the less we duty cycle that, the less we duty cycle the exhaust fans, the longer lasting they're going to be. So in your home, over the years, people will tolerate a 2 degree swing pretty easily. 4 degree, 6 degree, they tend to notice. Now if it's, say, a half a degree, what you get in a room like this is what we call chatter. On, off, on, off, on, off, on, off. It switches back and forth. There are times in Bay 3 you can hear that particular on-off system chattering away. It's set too tight. And it does chatter a bit at times. That's where I hear it there. But when it chatters like that, the motors really burn out because you're forever in startup mode, which is, as you've measured before, 200, 300, 400% current. That's a lot of current, it's a lot of heat generated, and it's dissipated as heat, burns the motor up. Motors don't last as long because of that heat. The electrical system has to be sized for more current. So everything gets warm, including all the cord wiring and all the components down the line, because it just generates, an average, more current. So that's the trade-off, deadband versus on-off switching times. What can you tolerate? Can you tolerate the chattering? Fine. Usually you can't. So then deadband is how much deadband can you tolerate, and that's how systems are set. Now in the case of relays, what happens when you switch on and off? Relays open and close. What's the number one failure mode of relays? Contacts shorting. Number 2, contacts burning open. It comes from the contacts switching on and off, because what happens when you take relays powered and you start to close them? What happens just before closing?
You arc.
They arc. It's like you scooting your feet on a nylon carpet and touching a doorknob. Just before you touch that doorknob, you get a little pop. Same thing with relays. There's a voltage like 120 volts across them. They will arc. Now it won't arc an inch apart, but less than a millimeter, it will slight arc. That's okay, it tolerates it. But when you have 100,000 of those, it finally burns through. Now, 100,000 sounds like a lot, but if you're switching once a second, that's 100,000 seconds. We get about 3,600 seconds a minute. Well, actually 60 seconds a minute, but then you have the day shift, times 8. You start to realize that number builds up to almost 1,000. You're not gonna last a year. Now, if your system has 10 relays, that's 1 relay a month. Pop has to be replaced, which means once a month the line's down, repairing the line. That's expensive. Now, if we, instead of breaking that second, we break a minute. Instead of doing 1 a month, now we're going to go once every 2 years. Well, that's keeping the line running, and that's why we have to worry about how fast we do it. So driving issue is going to be deadband. The most we can tolerate, as much deadband as we can tolerate, we want to slow the system down as far as turning on and off. And that's usually the driving force of calibration. One of the things you'll see an HVAC technician do when he goes to a home to tune up, so to speak, a furnace, they check the on-off switching time. They see what temperatures it does. They'll wait to turn it on and time it, see if it goes on too fast. Defrosting cycles, good example of this. You don't get this so much up north, but heat pumps up north, they always tune for, does it frost too much? Does it frost too little? Too little, the coils freeze. The outdoor compressor needs going to be replaced soon because it freezes up and it freezes up the refrigerator. Too often, you're not heating the house. Type of thing. That's just performance issues, much less destruction. So that's the key thing to watch here is on-off control system should have deadband wide enough to prevent frequent oscillation, what we call chatter, and still control the process variable. And you don't hit a specific set point. There's a high and low limit around it. That's what we can hit because that's what we can measure. It's like trees in Amazon. How many trees are falling this last hour? And since we can't see them, as far as we know, it's acceptable. Does anybody find a number of trees falling in the Amazon unacceptable? This last day? No, we should go measure it so you couldn't see it. If you can't observe it, you're not gonna control it. That's a key, no matter if it's on, off, or proportional. That's kind of what they look like. Looks like a motor control center. You can see incoming power always up top. You see the relays here, probably motor drives here, a few other components. And of course, there's a lid where you'll find most of the switches. And these trays here to run all the cabling in. That's a run cable. Notice it's all squared off. Looks very nice. A lot of you have heard me say squared off. This is how it would be done in real life, so you don't see it. It looks very nice. Looks very neat. If you have a little excess cable, you put it next to the tray. So 2 switches maintain level. As you can see here, high level switch. These are still kind of like float switches, and actually the control we have is a float switch. We have a pump. There's a valve here for draining, but it's a solenoid valve. In the pump here, we also have in between both solenoid valves and a diaphragm valve. Ladder diagram, you recognize these by now. Solenoid, that's your drain, your pump fill, and control relays that are built on. LS1, LS2, you'll find it on the lab. And this is your lab. SS1 for start and stop. Turns on a relay, the relay turns on the system and goes. I think we pretty much know how to do that, so you're going to wind up doing this in the lab and going. This is your basic on-off operation. And more description of what happens here on this. We've already gone through this. Any questions on off? Probably a good point to stop. And next week, I'm going to talk about proportional, and I'm going to get into this performance bit, is how they call it.